Why does gravity slow down time? My first forays into this topic were to consider an elevator with light coming up from the bottom. Okay, this wasn't a true elevator, but rather an accelerating box somewhere entirely outside of a gravitational field. If the box were accelerating upward, the light would be emitted from the bottom of the box in one frequency and be absorbed at the top of the box in a lower frequency. I have an animation of this phenomenon at Spoon-Fed Relativity. On this website, you can see a couple of different imaginings of the situation. In the first, we imagine an elevator where the frequency of the photons is constant from watching both inside and outside the elevator. In this situation, the wavelength becomes shorter and shorter as the elevator accelerates upward. But the frequency stays the same. You can hear when I snap as the photons leave the bottom of the floor. The actual frequency between them remains roughly constant. Alright, in the second imagining of the situation, I apply all of the relevant effects of special relativity. Lorentz contraction basically solves the issue of the changing wavelength over time. Well, you can see it makes the effect a lot less dramatic here. I'm doing a Galilean transform of the elevator back from the stationary frame. Which means that this isn't really what you would see on board the elevator. Of course, from inside the elevator, it won't look like it's contracting and then elongating. To see what was going on inside the elevator, you'd need a Lorentz transform back from this, not a Galilean transform. Right now, you can see that there's first one photon in the elevator, then two, and then three. Well, we see two now, and then there's going to be three. If we did a Lorentz transformation back to the reference frame of the elevator, you would actually see dramatic changes. You would not actually see dramatic changes in the photon density over time, but you would still see that the distance between the photons was slightly greater at the top of the elevator. Now, the question is, would you measure the frequency of the light to have slowed down at the top if you were in the elevator? Yes, I think you would. But what does that mean? You're looking down at something that happened down on the floor of the elevator, emitting a light in blue, and you're at the top of the elevator receiving a light in red. What are the implications of that? The implications are that time is actually going slower on the floor of the elevator. Now, I gather that further analysis of this accelerating elevator idea can be gleaned by looking up something called the Rindler coordinate system. Here's the Rindler coordinate chart here. But what you need to imagine is this thing doing a hyperbolic rotation over time. The hyperbolas represent different levels of or floors of the elevator, and the slanted lines represent planes of simultaneity. Okay, but when I say they are planes of simultaneity, they are only marked off in seconds in one place. So here, where it says x equals 1, these slanted planes will rotate past the horizontal in 1 second per second. But here, where it says x equals 0.8, the rate is 0.8 seconds per second, and he's experiencing 20% slower time. Here, where it says x equals 0.2, this guy is going to be experiencing time 80% slower than the guy up here at x equals 1. This is all assuming that they're standing in the same structure. This is a single elevator that, from this point of view, it's accelerating along this curve, and from this point of view, he's accelerating along this curve, and it's accelerating at different rates all the way along. Now, for this person here at the point known as the Rindler horizon, time is not passing at all. This is what you would call instantaneous acceleration. This person, you could think of it as going from 0 to 99.9999999% of the speed of light in a single collision, for instance. Here's sort of an animation of the Rindler coordinate system with 4 additional quadrants. This is something a lot like the Rindler coordinate system, but it's not quite. I was not modeling the Rindler coordinate system here, but just the concept of the Lorentz transformation. Here's sort of an animation of a Rindler-like coordinate system, but with 4 additional quadrants. This is something like the Rindler coordinate system, but I was not modeling the Rindler coordinate system here, but just the concept of the Lorentz transformation. If it were a model of the Rindler coordinate system, I wouldn't have a bunch of parallel horizontal lines coming through, but rather I would have a single set. Instead, I would have a bunch of slanted lines extending to the right only, to the right only from the single point at the origin. These slanted lines would sort of rotate clockwise around the origin as time passed from the I guess you can follow this. You can follow this intersection here down from the plus 45 degree angle to the negative 45 degree angle. Actually, I think now that I look at it, if you ignore all the other lines except for the slanted lines that have the little balls on them, you can see the lines that you can essentially see the lines that were marked out by Wikipedia's image on Rindler coordinates. Of course, I'm able to show a lot more of them here since they fade in and fade out as they go by. Well, essentially I'm showing an infinite number of them. The density of the lines tends to go to infinity as you reach as you get closer to the speed of light here. Yes, you can see here that those lines seem to just sort of converge on each other in the Wikipedia image. Now, all of that is only introduction, though. I have been talking about an elevator accelerating through space in a region of no gravity. In that situation, we can be reasonably certain, based on our arguments of special relativity, that time goes faster at the top of the elevator than at the bottom. So we're going to invoke the equivalence principle here, which states that the gravitational force as experienced while standing on a massive body such as the Earth is actually the same as the pseudo-force experienced by an observer in a non-inertial accelerated frame of reference. In other words, the effect of gravity should essentially be the same as the effect of acceleration. Now, the only real big difference is that when we were looking at the Rindler coordinate system, the acceleration of the entire system was the same. Well, that's bad wording. No, it wasn't the same. It was rigid, with the bottom of the elevator accelerating instantaneously, and the higher and higher parts of the elevator accelerating slower and slower. So while instead of modeling the entire structure of a huge Born-rigid Rindler elevator structure, we just model different chunks of it. For instance, in every 10-foot section of elevator, time is slowed down by a small factor as you go from the top to the bottom. Each 10-foot section of elevator may have a slightly different gravitational field, and thus it would have a slightly different time-slowing factor. but by taking the product of all of those factors and from all of the different gravitational fields from the surface of the planet into space, you can get a numerical value for how much the gravity of the planet slows the time. So this essential idea is worked out in Reflections on Relativity, and I worked out a lot of the math myself on physics forums a few years ago. I guess I did it right because nobody ever jumped in pointing out obvious errors. Either that or it was so boring nobody cared.